All right, let's dive into a really cool puzzle today. Imagine you've got this complex map full of points and one-way connections. Our job, yours and mine, is to hunt down and count a very special kind of route called a Fibonacci path.
So here's how we're going to tackle this. First, we'll get a handle on what this puzzle even is. Then, we'll see why the most obvious approach is a complete dead end. After that, we'll get to the real aha moment, build up our solution piece by piece, and then put it all together in the final algorithm.
Okay, so first things first. Before we can solve anything, we've got to know the rules of the game. Let's define exactly what we're up against.
So what in the world is a Fibonacci path? Well, the name itself gives us two huge clues. We've got to understand both parts, the path and the Fibonacci, to really get anywhere.
First up, our playing field. This is what's known as a directed graph, but don't let the fancy name fool you. Just think of it like a city map, but every single street is a one-way street. You can only go in the direction the arrow points. Simple as that.
Okay, that's the path part. Now for the Fibonacci part. When you hear Fibonacci, you probably think of that classic 1, 1, 2, 3 sequence. But here's the twist. We're talking about a generalized Fibonacci sequence. That means you can start with any two numbers you want, say 5 and 8. The next number has to be 13, then 21, and so on. The rule is always the same. Each new number is just the sum of the two before it.
So let's put it all together. Our mission is to find every single path on this one-way map that doesn't repeat any points, has at least two stops, and here's the kicker, the values at each stop have to follow that generalized Fibonacci rule. And we don't just find them, we have to count every last one.
All right, so we know the rules, and their first thought might be, okay, why don't we just check every single path possible? Sounds simple enough, right? Well, let's talk about why that's actually a terrible idea.
See, the potential scale of this problem is just mind-boggling. We could be dealing with a map that has up to 200,000 points and another 200,000 connections. The number of possible routes you could take through something that big, it's not just big, it's astronomical.
So if we try to just brute force it, tell a computer, hey, start at point A and just try everything, it would literally be running forever. Days, years, it's just not going to work. It's a computational dead end. We need a smarter approach, a much smarter approach. And this is where things get really interesting. This is the aha moment. Instead of trying to smash through the problem with brute force, we're going to find an elegant way to solve it.
The real question then becomes this. If we can't find all the paths by checking them one by one, is there a way we can build them efficiently? How can we piece them together without getting totally lost in an infinite maze of possibilities?
And the answer is yes. But the trick isn't some crazy complex formula. It's much simpler and much more profound than that. The secret isn't about what paths to check, but the order in which you build them. It all comes down to the order of operations.
So here's the big insight. Imagine any one-way street going from point U to point V. To figure out the paths that end at V, it would be super helpful if we already knew everything about the paths ending at U, right? So what if we process the connections based on their destination? If we sort all the one-way streets by the value of the point they're going to, from smallest to largest, we create this perfect logical flow. By the time we get to any point, we're guaranteed to have already figured out all the paths that came before it. It's brilliant.
And once we have that sorting trick up our sleeve, we can unlock a really powerful technique called dynamic programming. The idea is super simple. It's like building with Legos. You don't build a giant castle by sticking one random brick on top of another. No, you build smaller sections first, a tower here, a wall there, and then you connect those completed pieces. Dynamic programming is the same idea. Solve smaller pieces of the problem and use those solutions to build up to the final answer.
So how do we do that? Well, for every single point on our map, we're going to give it its own little notebook, a memory bank, if you will. This bank is going to keep track of all the valid Fibonacci paths that end at that exact spot. And inside that notebook, it's basically a little table. It's going to say, okay, for this point V, I know that 12 valid paths ending right here came from a previous point that had the value 5, and maybe 3 paths ending here came from a point with value 20, and so on. It's a perfect record of how we got to this point.
Okay, so how does this actually work in practice? It's surprisingly simple. We're going through our sorted connections one by one. Let's say we're looking at an edge from U to V. For the path to be a Fibonacci sequence, some previous value plus the value of U has to equal the value of V. So what's that required previous value? It's just simple subtraction. AV minus AU. Now, all we have to do is peek into Vertex Use Memory Bank and ask it, hey, how many paths do you have that came from a vertex with that exact value? Whatever number it gives back, boom, that's how many new, longer Fibonacci paths we just created.
All right, so we've got our secret weapon, the sorting, and we've got our main tool, those memory banks. It's time to put all the pieces together and lay out the final plan of attack.
Okay, here's the whole shebang, from start to finish. Step 1, we get everything set up. Our total path count starts at 0, and every vertex gets a fresh, empty memory bank. Step 2, the crucial part. We sort all the connections. Now, step 3, we just loop through that sorted list. For every connection from U to V, we do a few things. First, that connection itself is a new path of length 2, so we add 1 to our count. Then, we do our little lookup. We calculate the value we needed before U and ask U's memory bank how many paths it knows about that fit the bill. We add that number to our count. Finally, we take all these new paths we just found and update the memory for V. We just rinse and repeat, and that's it.
Now there's one last little detail. The total number of paths we find could be absolutely gigantic, like way too big for a normal computer number to even hold. So to keep things from breaking, we use a common trick called modulo arithmetic. All it does is keep the numbers contained within a specific range, using this big prime number you see here. It just ensures our final answer doesn't get out of control.
So, when you boil it all down, what's the big takeaway here? It's that sometimes the most elegant solution isn't a more powerful computer or a crazier algorithm. It's just looking at the problem from a different angle. A clever sorting order took a problem that was basically impossible and turned it into a simple, efficient calculation. That's pretty amazing.
And that really leaves us with something to think about, doesn't it? This core idea, that changing the order of operations can unlock a simple solution, it's not just for this one puzzle. It's a pattern you see everywhere. So I'll leave you with this question. Where else in your world, whether it's coding or just a complex project, could simply changing the order you do things be the secret key to solving the whole thing?